Hello, this is Dr. V.C. Sontake, Assistant Professor in the Department of Mechanical Engineering, St. Vincent Pallotti College of Engineering and Technology, Nagpur. I am going to teach the course Heat Transfer. Objectives of this video lecture are: we will be discussing law of radiation and will introduce a new property called as emissivity of radiating surfaces. Let us discuss law of radiation. It is also called as Stefan Boltzmann Law of radiation in detail. Stefan Boltzmann Law of radiation. This law was first found experimentally by an Austrian physicist, Joseph Stefan, in 1879 and later confirmed by Ludwig Boltzmann in 1884 by considering some thermodynamic concepts. That is why this law is also called as Stefan Boltzmann Law in the honor of both the physicists. The statement of this law goes as follows. This law states that radiative heat transfer rate per unit area from a black body or surface is directly proportional to the fourth power of its absolute temperature, and it is considered in Kelvin. In order to understand Stefan Boltzmann law of radiation, let us first consider a black surface having its surface at temperature Ts. It is exposed to the surrounding at temperature T infinity. There exists a great temperature difference between black surface and environment. So heat transfer will take place by radiation, which is a prerequisite for heat transfer to take place by radiation. The rate of heat transfer by radiation from the black surface per unit area is given by Q suffix B divided by A. Similarly, let us consider a non-black or real surface at temperature Ts having emissivity epsilon. Again, it is also maintained at the same temperature at which the black body is maintained. So by virtue of this temperature difference, heat transfer will take place by radiation. And let's say the heat transfer rate from this real surface to the surrounding is QA divided by A. That is heat transfer rate per unit area. So Stefan Boltzmann law of radiation is able to calculate this heat transfer rate by radiation per unit area for black surface as well as for this real surface. So mathematically, for black surface, Stefan Boltzmann law of radiation can be written as Q suffix B over A is directly proportional to Ts power 4 watt per meter square. If I remove the sign of proportionality, I will have to introduce one constant sigma. So equation becomes Q suffix B over A is equal to sigma Ts 4 watt per meter square. Now this equation is the rate of heat transfer per unit area from the body by radiation mechanism. In this equation, Ts is the absolute surface temperature of the body in Kelvin and sigma is constant of proportionality. It is also called as the Stefan Boltzmann constant and its value is given as 5.67 into 10 to power minus 8 watt per meter square Kelvin power 4. Now, the heat radiated from its per unit area by a real or non-black surface at the same temperature at which black surface is maintained is less and can be given by Stefan Boltzmann law of radiation by the equation QA over A, Q suffix A over A is equal to sigma epsilon Ts power 4 watt per meter square. So, this is the rate of heat transfer by radiation per unit area for real surface, where the epsilon is called as emissivity of the real surface. Now, what actually is emissivity? Emissivity can be considered as the ability of the real surface to emit radiation from its surface. I can also say more will be the emissivity of the surface, more easily and more readily it will emit radiation from its surface. The value of emissivity is generally between 0 to 1. If the value of emissivity is 0, the body is not going to emit radiation at all. And if the value of emissivity is 1, the body will behave like a black surface or black body. It will emit maximum radiations under that condition. So for any real surfaces, the value of emissivity lies between 0 to 1. Let us consider the another variation of this Stefan Boltzmann law of radiation. To get that variation, let us consider a real surface having surface area As, surface temperature Ts, and emissivity epsilon. It is completely enclosed by another body or surrounding at temperature T surrounding. Surface temperature is much greater than the surrounding temperature. So, by virtue of this temperature difference, heat transfer will take place by radiation from this body to this enclosure. So basically what is happening here, the heat transfer is taking place from this body to the surrounding by radiation mechanism. So from Stefan Boltzmann law of radiation, the net heat exchange rate by radiation between a real body and its surrounding can be given by the equation Q suffix A is equal to sigma epsilon As into Ts power 4 minus T surrounding power 4. So this is the equation which will give you net heat exchange between two bodies by radiation mechanism. In this particular case, the medium present between the surface and surrounding is not going to affect the radiation heat transfer. Now, combine heat transfer by convection and radiation. Many times what happens, the surface temperature is generally very high as compared to the environment to which it is exposed. Under such condition, heat transfer rate takes place by convection which is quite obvious, but at the same time it also takes place by radiation as well. So there will be two modes of heat transfer by which heat will transfer from body to the surrounding if temperature difference between body and the surrounding is much greater. So heat transfer will take place both by convection as well as by radiation. Under such condition, the total or net rate of heat exchange by the surface to the surroundings by combined modes of convection and radiation is given by Q total is equal to Q convection plus Q radiation. So Q total will be Hc into As into Ts minus T infinity, rate of heat transfer by convection mode, and sigma epsilon As Ts4 minus T infinity power 4, the net rate of heat exchange by radiation mechanism. Further, let us assume the radiation or surface heat transfer coefficient HR is very similar to the convective heat transfer coefficient H suffix C. So I can have an analogy between convection and radiation mode. So Q radiation can be expressed in terms of Newton's law of cooling as HR As into Ts minus T infinity. If I equate this equation equal to the net rate of heat exchange by radiation, I will get the value of radiative heat transfer coefficient H suffix R is equal to sigma epsilon Ts power 4 minus T infinity power 4 over Ts minus T infinity. Now, considering the value of this HR, equation 1 can also be written as Q2 Q total is equal to HCAS into Ts minus T infinity plus HRAS into Ts minus T infinity. Taking some common terms out, the total heat exchange from the surface to the surrounding by radiation as well as convection mode can be given as Hc plus Hr into As into Ts minus T infinity. So this will be the rate of heat transfer by combined mode of convection as well as radiation. So summary of this video lecture is as follows. In this lecture we have discussed about the Stefan Boltzmann law of radiation to calculate heat transfer rate by radiation from black surface, from real surface, and the rate of heat exchange between the surface completely enclosed by another surface. We have also discussed the emissivity of the radiating surfaces. With this, I come to an end of this video lecture. Thanks for patient listening. Happy learning.